All right, now today, if there's any questions about the Kepler's laws, I'll be happy to answer. Then we're going to get into Mr. Newton, see what Mr. Newton's work is all about. Does anybody have any questions on Kepler's laws? So what did Kepler do? His first one, uh, was, thank you, Mina. Yeah, the recording is already on. So his first law deals with the position of the sun. It's at the foci of the orbit, and the orbits are elliptical. So two things he figured out in the first law, that the orbits are all elliptical, one. Number two, that the sun is at the foci of the ellipse. Two things. Then law number two, not very clear. Like what he's trying to say is that there is a relationship between the period that it takes a planet to go around the sun, sometimes referred to as a sidereal period of a planet. That to the power of 2 is related to the average distance to the power of 3. That's the law number 3. But law number 2 says there's a relationship between period and the average distance. Law number 3 expresses that relationship, right? It says p squared is equal to a cubed, because he doesn't know the answer yet. All he knows is that when a planet goes around the sun, as it approaches the sun, it speeds up. As it goes away from the sun, it slows down. Speeds up, slows down, like that, right? So he knows there's a relationship between a planet, how long it takes it to go around the sun, and the distance between the planet and the sun. Law number 3 is telling you what it is. And if I give you a number question there, I'll give you something simple, something that you can actually do with your head. You don't need a calculator. Like, I'm not going to give you 31.6 or something ridiculous like that. I'll give you something that has answers that are fairly simple to figure out. Like, we said Jupiter takes 8 years to go around the sun. What is this distance? So you say 8 times 8 is 64. Then you get a cube root of 64. What number times itself? 3 times equals 64. The number is 4, right? 4 times 4, 16. 16 times 4, 64. Something like that. I might even give you a distance and then ask you guys to get the period. That's probably simpler because all you have to do is to get the square root. You don't have to do the cube root, the third root. All right. All right, so let's get to Newton, man. Newton is the smartest man to ever have lived. At least that's what your book says. So the smartest man that ever lived? Sheesh. Who could this be? Well, this guy had a, pretty normal childhood. He was from a middle class, not that big a deal. And as he grew up, it appeared to be smarter and smarter and smarter, right? Because some people, these geniuses, they don't appear to be geniuses. Sometimes they're into themselves, so once they become an adult and they, interface with other people, then they go, oh my God, this guy is a genius, right? And I can tell you this, he did weird stuff, really weird stuff. Like as an example, one of the weirdest things he ever did, he stole somebody's manuscript, like the head of the Royal Astronomical Society of England. He had written a book, hadn't published it yet. He was still working on it. He went to his house. He broke into his house. He stole his book and he gave it to a publisher to publish somebody else's book. That's Newton for you. So that his friend, Sir Edmund Halley can get a hold of the information in the book. Now, that's not weird enough. Towards the end of his life, he was the head of the secret police in England. That's a big job. And then when they exhumed his body, they found out that he had Alzheimer's. So he had Alzheimer's when he was the head of the secret police in England. Now that's scary, you guys. That's really scary because, to two things, there's just not something you want to do. Get somebody that has got Alzheimer's to be head of the secret police. So God knows how many people got tortured, how many people got killed, because it was a secret police, right? Anyway, so eventually he's going to be a genius, right? As he grows up, he's going to be a genius and is sitting under the tree. This is a story, of course. He's sitting under the tree and he sees an apple falling on his head. So the apple falls on his head, and when he looks up, he sees the moon. So he sees the apple and the moon. So he says, the same force that dropped the apple on my head must be the same force that keeps the moon in orbit around the earth. And he was right. That's the beginning of him having intuitions about gravity. But before I get into gravity heavy duty, there's a few things that we do have to cover. One of the things that we have to cover has to do with mass and weight. So let's see what mass is and what weight is. You can write this down too. So mass is the amount of all the particles you have in your body. So all the stuff that makes me, like, there's atoms. I'm made of atoms. So all the atoms in my body, all the stuffing in my body, that constitutes my mass. That could be atoms, it could be molecules, that's all my mass. Now, weight is different. Mass doesn't change. If I go to the moon, my mass will be the same. Number of atoms in my body doesn't change, right? However, if I go to the moon, the gravity of the moon is a lot less than the gravity of the earth. It has to do with the mass of the earth versus the mass of the moon. So mass gives you gravity, but when you go to the moon, your weight is way, way smaller. So what is weight? Weight is the force of gravity on me standing here on Earth. So as I stand before you, my weight is probably 150 pounds. If I go to the moon, that changes. I probably become like 1/6 as much. What is 1/6 of 150? That'll be 25 pounds. I'll be 25 pounds on the moon. So I can jump around 6 times higher. I can throw a ball 6 times farther, right? So that's the difference between weight and mass. So weight is the force of gravity upon you on Earth. Because if you're falling, like you jump off an airplane, you're weightless. You don't have any weight at all until you hit the ground. Then you have weight. Mass is all the number of atoms in my body. So if you add up all the atoms and molecules in my body, that's my mass. That doesn't change. All right, now the first law is called the law of inertia. Now, Galileo talked about this. We've already talked about the law of inertia. Let's see what Newton has to say about it. It's exactly the same thing that Galileo said about the law of inertia. So what is inertia? Inertia is mass. So whatever has mass has this property. Now, they already tested this on atoms. I just read an article that atoms have already been tested. So let's take a look to see what the law of inertia says. So we say Newton, Mr. Fig Newton, Newtons.
Sorry, did you say inertia is mass or has mass?
Is mass.
Thank you.
Inertia is mass. Yeah. So law number 1 says an object in motion, an object in motion will continue this motion unless it is acted upon by an external force. All right, it may not seem like much, but it's a lot, what he's saying. So what he's saying is, if I throw this ball will go on forever and ever and ever with the same exact trajectory. So if I throw the ball, it will go for like this forever and ever and ever. But it doesn't. We know that. If I throw this ball, it's going to go down. That's because there's an external force on the Earth, and that external force is gravity. So gravity makes the ball go down, right? It's an attractive force. All right, so there's the external force. What if in space we have Donald Duck flying around? There's Donald Duck, and he's flying around. And what does he see? He sees a planet. So as Donald Duck's trajectory is like this, he would go like this if there is no planet here. But there's a planet here. So it changes his trajectory. He goes, shh. Now, why is that important? It's important because the Greeks used to think that objects that are stationary, they're in their natural environment, they're in a natural state. So this thing sitting here is in a natural state. But you see, this object is rotating with the Earth. The Earth is going around the sun. So this thing is not only moving with the Earth, but it's also going around the sun. And the sun is moving around the galaxy. So it's also going around the galaxy with the Earth and the solar system. And then our galaxy is moving, extremely fast as compared to the other galaxies. So we're all moving right now. You're not stationary. We're all moving right now. Like as you look at me, I'm moving at thousands of miles per second. Per second, I tell you. So I'm like Superman, except faster than Superman. Except you don't see it because I'm stuck to the Earth. And so we don't see it. We think that we're stationary. And that's what the Greeks used to think. All right. Any questions about this first law then? Now, I have a question to ask you.
I do have a question.
Yes, please ask.
Okay, so is the law of inertia wrong?
No, absolutely not. Absolutely not.
But it doesn't really work on Earth.
Oh, absolutely works on Earth. We said, unless it is acted upon by an external force.
Right.
So
and gravity is the external force.
This whole thing is the law, right? This whole thing is the law. It's not just objects will continue in motion. That's not the law of Newton.
Okay.
Yeah, so moving
So
the force is also part of the law.
Gotcha.
Yeah. But now I have a question to ask you. What is a force? We say external force. What is that? We say gravity is a force. What is that? So
No.
Just
So
anything
now-
that inhibits something from doing its natural course.
That's the majesty of Mr. Newton. For the first time in human history, he's going to explain to us what force is. No, you can't get any more basic than that. He's going to explain to us what force is. Sheesh, right? That's pretty impressive. But before we get to the second law, which is the basis of mechanics, right? I have to take 3 classes in mechanics. And I wasn't even a physics major, but I had to. 3 classes on just one little stupid looking formula is the basis of how we got to the moon, basically, this little simple formula. But before we get there, there's a few things that we have to cover before we understand everything about this simple formula even. So I'm going to give you an example here. And this is San Diego. SD is San Diego. And this is San Francisco, SF. All right, SF is San Francisco. I believe the distance between San Diego and San Francisco is like 450 miles. I've done that a few times. So this is 450 miles, right? Distance. Now I have a black Porsche. It's a 911. It's an older model, but I fixed it myself and it can go 100 miles an hour. And I painted it with a special paint so that the cops can't even give me a ticket. It's like a stealth car. So when they, bounce a radar off of me, the radar scatters, they can't even see me. I was going at 100 miles an hour, right? 100 miles an hour. An hour. I want to go to San Francisco, 450 miles. How long would it take me to get to San Francisco?
4.5 hours.
Yeah, that would be an answer that anybody would give, right?
It depends on traffic.
Thank you. That's correct. It depends on traffic also. But you see, here's what happened. So I went from San Diego, I went to Las Vegas to some gambling. And after Las Vegas, I went to Reno to see my ex-girlfriend. And after Reno, I went to Coalinga to Harris Ranch to have a steak lunch or dinner, whatever. And then after that, I went to San Francisco. So I didn't give you all the information then. All I told you was my speed. This is my speed. I didn't tell you I was going north on 5, did I? No. I didn't tell you I was going to go 101. I didn't tell you anything. I just said, that's my speed. Here's the distance, right? All right. So what is this then? Well, this is called speed. So speed is the distance traveled in time. That means I can go around and around, like I can go around like this. I'm not going anywhere. Maybe I'm going 100 miles an hour, and maybe I want to go to the store, but at this rate, I'll never get to the store because I'm going in circles. So what is it that I'm not giving you? I'm giving you the speed, which is the distance that I'm traveling in time. So in 1 hour, I'm going 100 miles. That's my speed. Now, there is something else called velocity, and velocity is the speed, all right, but it has direction. So I go, I'm going 100 miles an hour due north, something like that. So this is called velocity. Velocity is, that's all it is, speed with direction. So speed with direction is called velocity. So what's an example of that? 100 miles per hour due north. That'll be it. So that'll be 100 miles per hour due north, or northeast, or northwest, or west, or east, or what have you. So if you're taking other math classes, you know this is called a vector. So a vector has direction, and speed doesn't have direction. So velocity with direction, speed has no direction. All right. So I'm going 100 miles an hour. Now, I want to accelerate. I want to go faster. It's not 100 miles an hour is not enough. So I'm going to go 105 miles an hour, 110 miles an hour, right? But it takes me 1 second to go from 100 miles an hour to 110 miles an hour. So what is my acceleration? How much did I accelerate? Huh. What is acceleration then, right? So we want to figure out what acceleration is now. So acceleration is the change in my velocity in time. So that's the change of a velocity in time. Remember, I was going at 100 miles per hour. So I'm going at 100 miles per hour due north, right? And then after 1 second later, I'm going 110 miles per hour due north. All right, so what is my acceleration now? Let's see, that would be 10 miles, right? 10 miles per hour. That's how much faster I was. That's my speed is increased, right? From 100 to 110 miles. I'm still going due north, so this is velocity, it's not acceleration. And then that's change of velocity happens in 1 second. So that will be 10 miles per hour per second due north. And that's called acceleration.
Could
Yeah.
you, I can't see the bottom.
You can't?
Mm-mm. It's
Oh,
cut
oh.
off halfway.
Something's wrong with your camera then, because I'm giving it to you here.
Oh, there it is. There it is.
You can even see that.
Now I can see it.
Okay,
Thank you.
welcome.
Are our people pictures in the way?
Huh?
No.
Oh,
No.
yeah. For me, I just have to move the
Yeah,
us
just
out of the way.
you got to get used to Zoom, I guess. You know what a pain. I hate those little pictures that Zoom has. It's always on the way. All right. So now, what if I went 100 miles per hour due north, and then 2 seconds later, I was going 110 miles per hour due north. Then I'll be accelerating 5 miles per hour per second due north, right? Because it took me 2 seconds to accelerate 10 miles, and each second I accelerated 5 miles per hour per second due north. Okay, now, a question to ask you guys. And this is pretty key, actually. So let's see. You guys have seen those races, car races that they have. Mostly, like in the South, like in Atlanta or something, they have car races. What do they call those car races?
Track race?
NASCAR?
Not NASCAR. Yeah, that's it, NASCAR. All right, so here's a NASCAR track. And it's a nice and round NASCAR track, all right? And here's a car. Here is a car. And it's going at, let's say, 180, miles per hour. Constant. It doesn't change the speed. It's not, going faster or slower. Is that car accelerating if it keeps its speed at 100 miles per hour?
No.
No.
Right? It turns out that it is accelerating. Why is it accelerating? Let's take a look. Because it says acceleration is a change of velocity in time, right? So change of velocity. What is velocity? Speed with direction. Now I'm changing my direction constantly, so I'm constantly accelerating. This is a constant acceleration. So how do you know which direction you're going? When you draw a line from the center of the track to the position of the car, you're going here now. Later on, you're going this way. You're going this way. So you continuously are changing your direction. Now, this is not a special force. This is a force we call centripetal force. I don't want to get into it very deeply, but let me just give you an example. Like when you guys enter the freeway, right? You're entering the freeway and you want to go left. Have you ever felt anything like you're going left? As an example, if you have a coffee on your dash, it flies that away. If I'm going this way, like I'm turning this way, doesn't your body get shoved against the door?
Right.
Yeah, that's the centripetal force. So it's not a real force. It's just, acceleration away from the center here. So that's the acceleration. So you constantly accelerate. This is a constant acceleration. Now, why am I telling you all this?
I don't.
Because of the second law. Second law, Mr. Newton's second law is his masterpiece. It explains what force is, right? So let's see what force is in just simple terms. What is force? Right. So we say Newton's second law. Law number 2. It says force is equal to mass times acceleration. Mass times acceleration. Now you've seen this many times probably, but I don't want to assume that you even went to school. Maybe you were homeschooled. Who knows, right? So you've seen this, perhaps you've seen this before. It says F is equal to M mass times A acceleration. F is equal to ma. This is Newton's second law. This is also the definition of what force is, which is kind of impressive definition of force. Yeah. So what is this saying force is? So force, it says, force is that which accelerates mass. Force is that which accelerates mass, right? So for the first time in human history, somebody's actually explaining to us what force is, right? Force is that which accelerates mass. Definition of what force is. So if I touch this thing here, oh, look at that, it's accelerating. If you throw the ball, it's accelerating. It's going from like nothing in your hand, etc. So, of course, initially, it's moving with the earth and everything and going around the sun and everything. But even if you look at it that way, still, I'm giving it acceleration. I'm changing, right? Either its direction or I'm changing its acceleration, right? I'm changing its speed or its direction, which is velocity. Any change in velocity is acceleration. Either acceleration or deceleration, slowing down, right? Either way. Either way requires a force. Okay, so let's see what the heck all of this means. Force is equal to mass times acceleration. Okay, let me tell you, when
I'm sorry, so is the deceleration also assumed therein, or?
yeah, deceleration is the same as acceleration. You're still changing your velocity, right? If you
Okay.
look at the definition of acceleration, is a change. It doesn't say speed up, right? So that's also considered acceleration. Deceleration, acceleration.
Okay, thank you.
You're welcome.
Yeah, good.
When I go downtown, like when I go to a ballpark and watch the Padre game or something, I kind of feel uncomfortable at 9 o'clock at night. Go to my car, it's all dark and everything. So what I do, I have my keys. Now here I have my flashlight. So as I'm walking, if somebody attacks me, what am I going to do? Well, I want to have more force to defend myself, right? So how do you get more force here? How do you increase your force? Well, this is something called a direct relationship. A direct relationship. See what that means, a direct relationship. So we have a force here, right, on this side. And we have mass and acceleration on this side. This is telling us that it's an equation. It's equal. So one side is equal to the other side, right? One side is the same as the other side. So now, if that's the case, and you have an equation, and you have multiplication here, first of all, you don't even have to use this multiplication sign. You can just scrap the multiplication sign. You can just say F is equal to MA. It's assumed. If you say MA, it's assumed. With multiplication, you can do that. You can't do that with division, though, okay? Don't do that with division. Multiplication, you can do that. So you can say F is equal to MA. Now, so this side is equal to this side. And I can do whatever I want to either side. I can multiply F times something, but then I have to multiply this side times something. So twice as much force is equal to twice M times A. 10 times force is equal to 10 times mass times acceleration. So I can do the same thing to both sides. So I'm going to divide both sides by mass now. All right, so I'm going to divide this side by mass, and I'm going to divide this side by mass. All right, because they're equal. So if I do that, then mass on this side cancels out the mass on this side. So now we have F divided by M is equal to acceleration. So I can say A, acceleration, is equal to force divided by mass, like that. So I get another version of the same exact equation, but now it says acceleration is equal to force divided by mass. All right, so we have force is equal to mass times acceleration, right? The force is equal to mass times acceleration. And acceleration is equal to force divided by mass. All right, let's see what the heck all this stuff means. So here, this is a direct relationship between force, mass, and acceleration. So if I want to have more force, if I want force to increase, what can I do? I can either increase my acceleration or my mass. Either one will give me more force. All right, so let's see how that works. So here I have some power here, right? Some force here. All right, now if I grab this mass and hit somebody with it, I can do a lot more damage. Why? Well, because my mass is just went up. I have flashlight and my hand, right? Otherwise, I would just have a fist. So fist plus this, my mass is going up. If my mass goes up, the force automatically goes up. What about acceleration? Can I just keep the mass the same and instead accelerate, right? Yes, that also works. That's called karate, right? Karate. So karate is the same thing. You just accelerate. All you're trying to do is to get more force. So if you want more force, you either accelerate, karate, or you can increase your mass and get a metal glove or something. You have a lot more punch power. Now, there is something here that I should tell you. When you use karate, like you go break a piece of wood, there's also something called impulse power. This impulse means how long do you have contact with this piece of board? So if you watch the movies with people doing karate, like they break stuff with their head, they go, whoa, like that, right? What is that? Whoa. Well, that's the duration of contact. So you don't just go like that. You hit it, and then you continue to go through it. You go, right? And so that's called impulse. You've heard Captain Kirk on Star Trek say, Mr. Whatever, impulse power. That's impulse power. They're given a little bit of impulse, right? Like the engines come on maybe 1 second at a time, just making the spaceship go just a little faster. You know, just get off the
Instead
port.
of warp speed.
Huh?
Instead of warp speed. You're just giving it
right.
a little gas.
Yeah, just to get out of the station, you know, they're always parked someplace in the station. And then to get out, you get impulse power. That's the duration of the force. That's impulse. All right, so now let's see what else. So if I want to accelerate now, what do I do? Okay, so you want to accelerate. Now listen carefully, please, because this is going to come up again. In this case, if I increase my force or decrease my mass, I would accelerate. So increase my force, you can see, like if you're going in a car, you put your foot on a gas pedal and your car will accelerate. So that's one way of doing it. Increase your force. Now, I can also decrease my mass. Well, what does that mean? Well, remember James Bond movies? James Bond has this beautiful car, Aston Martin. And this Aston Martin, the bad guy sits next to him. He's got a gun to Bond's face. He says, park over there. I want to talk to you. So instead of parking, he presses a button and the bad guy gets thrown out of the car, right? He gets ejected. He's got an ejection button. When the mass is ejected out of the car, he accelerates. He's got to go faster. Or you're driving a truck full of watermelons and the back of the truck opens up. The watermelons are falling to the freeway. You accelerate. Or you have your entire family in your car and you're asking me, why isn't my car accelerating anymore? It's because you have more mass in your car, right? So the more family you have in your car, the more difficult it is to accelerate. So I guess you guys can see what I'm talking about here. Now, here's the key
Professor,
point I'm trying to make.
I have a question.
Point and I'll answer your question. So
Okay.
here, there's an indirect relationship. This is an inverse relationship. So we can say acceleration is directly related to the force, inversely directed to the mass. So if the mass goes down, acceleration goes up. If the force goes up, acceleration goes up. So between acceleration and force, there's a direct relationship. More force, more acceleration. You put your foot on the gas pedal. Here, the smaller m gets, the bigger acceleration gets. So this is an indirect relationship. This is an inverse relationship. There you go. What's an inverse? Well, inverse of a number is 1 over that number, like 2. Inverse of 2 is 1/2. 1 divided by 2 is the inverse of 2. So this is 1 divided by n, right? This would be inverse of n. So anything 1 over anything will be inverse of that thing. So 1 divided by b will be inverse of b. What's the inverse of 10? 1 divided by 10. That's an inverse of 10. Sorry, I'm teaching you math, but I just want to make sure you guys don't get lost because your math is bad or something. Just giving you a little review. No, I'm so sorry now. Ask your question, please.
So with your truck and watermelon example, you're saying if the watermelons go out of the truck goes faster?
Correct. Accelerates.
Accelerates. If something so say a truck is going 50 miles per hour and something or like a bowling ball is shot out of the truck with the same force.
We're just talking about stuff dropping out of the car. We're not talking about shooting. We're not making a rocket here. We're just trying to see what happens if the mass is lost out of the car. We'll get to the rocket power right now. After we're done with the force is equal to mass times acceleration, then we're going to see how rockets work.
Professor, do we need to know the term impulse power?
No, you don't need to know impulse power, but for your information, you can understand why karate works. Because not only you're accelerating, you also have to go through it. Your teacher would tell you, it's like, don't just go bang, bang. That's not going to happen. Nothing's going to happen to the wood.
Yeah, follow
You
through.
go through the wood. You hit it and you go,
And that is what impulse power is? Following
It's
through?
the duration of the force, how long you're applying the force. That's called impulse.
Thank you.
You're welcome.
Professor, would it be the same, because you mentioned it the same for the deceleration, would that be like the same formula for the deceleration?
Yeah, it's the same exact thing. Yeah. Same exact thing. All right, so that's the second law. The second law is telling us a lot. It's telling us how things move. It's telling us what force is. And it's telling us that there's a direct relationship between force, mass, and acceleration. Acceleration goes up, force goes up, mass goes up, force goes up. On the other hand, acceleration has an inverse relationship with mass. The smaller the mass gets, the bigger acceleration gets. But it has a direct relationship with force. The bigger the force gets, the bigger the acceleration is. All right, let's see the third law now. We got a little time. Okay. Now the third force, law number 3. This one you've heard before. It says, remember, for every action, there is reaction. Reaction equal and the opposite direction. All right. So this is not so obvious because on Earth, it doesn't really work this way, right? It's not that easy to see this on Earth. It works the same everywhere, but it's a lot easier to see Sandra Bullock in that movie Gravity do it than it is in this room. So here, I'm going to press on this wall. So I press on the wall, and I'm really trying hard, and nothing is happening. I should be going backwards, right? But I'm not. Why? Because there's friction between my shoes and the ground. That doesn't let me. So if I was in an ice skating rink, I would go backwards. If I go do this, I go, ooh, I get out like that in the ice skating rink. And that explains why the fights in hockey look funny. Because if you hit somebody in hockey, what happens? Well, you hit somebody, they go that way, you go this way. So it's like the opposite, right? You hit him, he goes away from you. You don't get the chance to hit him the second time. So next time you watch hockey, take a look. They grab each other like this and they pull them down and then they go like that. That's a hockey fight. So they go, oh, like that. So they pull them down because they don't want them to go backwards. They want to hold on to them. And they go like that because the guy's not going to fly into space. He's going to stay put. That's what the hockey fights are all about. All right, what else? Well, this is a basis of how rockets work too. So I'm going to make you guys a rocket with bowling balls. All right, here's a rocket. And on this rocket, I have me and lots of bowling balls. Here are bowling balls. Bowling balls everywhere. All right, so now I'm going to grab a bowling ball and throw it in the back of the rocket like this. Here's a bowling ball. The faster the bowling ball exits, the harder the rocket goes forward. That's how rockets in space work. They don't have a jet engine that then grab air and push it behind them and stuff. So basically, it's the third law that makes rockets work. The more force you put this away, the faster the rocket goes that away. Now, normally they don't use bowling balls. What they do is to have gases. So they burn hydrogen, oxygen, and they have like a little nozzle here. And they eject gases at high speed here. And that allows the rocket to go forward in space. Right, that's how rockets in space work. Now, what if this is an asteroid or a comet and it's outgassing? You know, it's like inside of comets, there's a lot of ice, and this ice becomes gas in space. There is no liquid in space. You need to be on Earth to have liquid, right? So you can have liquid, you have to have an atmosphere. So in space, no liquid. They go from ice into gas directly. It's called sublimation. Regardless, so if a comet does that, and a comet maybe looks like this, and it starts outgassing like that, and then this thing here is going to maybe start rotating this way. So the objects start moving just because they have this internal, you know, explosion or something beneath the surface of a comet. Happens all the time. That's why you never know when comets are coming in, when they're going out, because they have this ice that sublimates, becomes gas directly without becoming liquid. All right. All right, so now I just showed you how rockets work. Now, last thing.
A question. Can I ask a question on that?
Of course.
Is it the mass of the gases leaving that then propels the rocket forward?
It's whatever you have, right? It says for every action, there is a reaction in the opposite direction. So it doesn't matter what you have. If you don't have something that is massive, then you can have something that is light. You need to shove it in the back at a much higher speed. So yeah, you know, gas doesn't have much mass. But if
Right.
you shoot it out really, really high speed,
Okay.
right? It's like
So
a
it's the
jet,
speed of the gas.
jet
Thank
of
you.
water or something, you know? Have you ever
Okay,
played with water and like made a little jet with your hose? You push it to the doggy and the doggy starts flying around. Well, you would if you took a fire class, like a fire safety class or something. You used to play around with the hose. Those are hoses. All right. So now, law of gravity. So gravity. Now, before I get to gravity, there's one more thing I need to tell you. And that's what a constant is. So what is exactly that? It sounds like A constant. A constant. What's a constant? Something that doesn't change, right? Constant. Okay, so it's a constant. All right, a constant. What's an example of a constant? Well, it turns out that if you have a circle, and this applies to every size circle in the entire universe, this is called the circumference of the circle. We go all the way around and measure this. This is called the circumference of a circle. This is called the diameter of the circle. The diameter, circumference. If you divide the diameter of a circle, if you divide the circumference of a circle by its diameter, you get pi. That pi that you see, when I ask you, say 3.14 is not really 3.14. It's the ratio of the circumference of any circle, any size. You can have a tiny circle, you can have a big circle. It's kind of magical, actually, right? So the circumference of a circle divided by the diameter of the circle. That's always pi, regardless. That's a constant. It never changes. So pi is like 3.14 da 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 da. I don't know how many decimals we've gone so far, but there's quite a few numbers after the decimal that we figured out. We need to know it as exactly as we can. So it goes like 150 numbers after the decimal, you know, so that's a constant, all right? So gravity, it says force of gravity.
I'm sorry, what was the original word? Constant?
Constant,
Oh, well, a constant. Oh, sorry, you weren't
a constant, yeah.
constant. Yes.
A
Sorry, I thought the original word we were talking about was a constant, and it is a constant. So sorry.
constant. These are
Constant.
all constant, something that doesn't change. So I'm going to give you a constant here because there's a constant in here. I want to make sure you guys know what a constant is before I give you a constant. So force of gravity is equal to G, capital G. This is called gravitational constant. Gravitational constant. Now, this gravitational constant has to do with the mass in our universe. And so the way they actually figure it out is like this. They get two balls, very massive. This big one is massive. This small one is not that massive. And you know, they're attracted to the Earth, right? And also the Earth is attracted to them, by the way. But anyways, so they have these two balls. And they want to know how much this ball attracts this little globe here. And it turns out that has to do with the mass in our universe. In other words, protons, electrons, stuff like that, right? That's what makes up the mass. So in this case, it's a constant of gravity. You find it in your book, you don't really need it. It's this weird number you'll find at the end of all the astronomy books. What it is, though, like I just explained, it has to do with the gravitational force that even one single proton has. So if you have one proton, like the nucleus of the proton, you have gravity. As soon as you have any kind of mass, gravity, right? So that's a constant. But I want you to kind of ignore this. Know that it's here, but you can ignore it because it doesn't do anything. It's a constant. It's always multiplying the same exact number. So it's nothing to worry about. All right, so then we have mass 1 times a mass 2 divided by distance between masses. That's mass 1 and mass 2 to the power of 2. So I'm going to rewrite it so you can see a little easier now. So normally you find in the book written like this. It says force of gravity is F of G. Thus force of gravity is equal to m1 times m2. Remember I said you don't have to need this multiplication sign. m1, m2 divided by d, the distance, to the power of 2 times itself. All right, so force of gravity, remember, it also has a g. I didn't even put the g down. See, it's not that important, right? The g is just multiplied times the whole thing. So what we see here, that I can tell you, force of gravity is directly related to the masses. Either one of the masses goes up, gravity goes up. So like the mass of the Earth goes up, I feel more force of gravity. That's all. That's what he's saying. So if the force, if you want to see how much force the gravity has, you look at the masses. The more mass you have, the more force of gravity. Now, what about the distance? Well, the distance is also important. If you get far from the moon, I don't feel so much gravitational force. The closer I get, the more gravitational force I experience. However, it's not directly related. This is an inverse square of distance, which means if the distance increases, force of gravity decreases with the square of that distance. So if d goes up 2 times, right? 2 times, force of gravity goes down 1 divided by 2 to the power of 2, right? So it becomes 1/4. You see, it doesn't go down half as much, quarter as much, right? So if the force of gravity goes down 3 times, what happens? 3 times. How much does the force of gravity decrease now?
1/9.
9 times, right? 9 times or 1/9, whichever you want to use, right? So maybe 1/3, 1/3 to the power of 2, or 1/9 as much gravity. What happens if you have quadruple your distance? You go 4 times farther from the Earth. The force of gravity goes down.
16 times.
That's right, it goes down 16 times if you go 4 times farther. All right, so let me show you that in graphics. Let me just show you. All right, so let's take a look. Example bonanza. I'm not going to give you too many things on this. I'm afraid that you guys' math is probably not the best, so I'll try to take it easy on you guys. All right, so here's the Earth. Draw the Earth in blue, maybe. Here's the Earth. Here's the center of the Earth. And here I am on the surface of the Earth. Mass of the Earth, I can call either m1 or m2. Remember, I'll put the formula here. Force of gravity is equal to the g, ignore, m1, m2, divided by d squared. All right, let's see what everybody is. So my mass is m1. Mass of the Earth, m2. Simple enough. Now the distance between the center of the Earth to me is d. So if the Earth was bigger with the same mass, if it was like less dense and it was just puffy, then you would have a lot less gravitational force. Now what happens if I move away from the Earth? So now I go over here. This is 1D. Here's another D. So now it's 2D, right? I just went twice as far away from the center of the Earth. Basically, I'm going to go to space, and I want to see how much the force of gravity is going to decrease. Remember, the force of gravity is also weight, right? So let's see how much my weight is going to drop if I move twice as far away. Okay, so instead of D, I'm going to put in 2D to the power of 2. Right? I just went from 1D to 2D. So this would be 4D squared. That means force of gravity is going to drop 4 times. I'm going to weigh 1/4 as much if I go twice as far away from the Earth. All right, let me go 3 times farther now. Let me go over here. There's 1D. There's another D. Not another D yet. So D. This is 3D. How much does the force of gravity decrease if I go 3 times farther from the Earth? Well, let's see. Maybe 9D, right? It'd be 3D to the power of 2 or 9D squared. So force of gravity goes down 9 times if I go away 3 times farther, right? So if I go away twice as far, my weight will decrease 4 times. If I go 3 times farther, it go up 9 times. What if I went away from the Earth 5 times? How much does the force of gravity decrease?
25.
25 times. So if I go 6 times farther, how much does the force of gravity decrease?
36.
36 times. If I go 10 times farther, it'd be
100.
100 times. Very good. All right, excellent. All right. Now, you guys, one last thing before we leave, though, and that is this. Actually, I need to tell you guys something about the quiz, too, before we leave. But one more thing here is the center of gravity. The center of gravity means that if you have the, let's say, a teeter-totter, all right? Here's a teeter-totter. And you have a child sitting here. All right, and there's a kid sitting here. And then there's an adult sitting here. Okay, what happens now to the teeter-totter? You've experienced that before, right? Yeah, it's a bummer, right? This is a bummer for sure. Like me and my dad. Well, my dad says here, I'll be up in the air. I can never do anything. It'll be the end of fun. That's not fun, right? So if you move the pivoting point here, right? If you move the pivoting point, then like over here, then you see this will work. Now this will work. So why did I move this? Because that's the center of mass. Inherently, we all know how this thing works. Now here is the moon and the earth. So let me put the moon and the earth here now. So here is the earth. Here is the moon. Let's put them on a teeter-totter. Where should the teeter-totter go, right? Here it is. Now, instead of people, we have 2 moon on the earth. So it turns out that the center of mass of the earth and the moon end up being inside of the earth. Over here. Like that. So that's the center of mass of Earth-Moon system. the center of the Earth-Moon system. So what does that mean and why is it important? Well, this is it. So I have the Earth here, and I have the Moon here. And I'm trying to figure out the teeter-totter thing. And what happens is this. See, the Moon doesn't go around the Earth. You think it would, but it doesn't. The Moon goes around the center of mass of the Earth and the Moon. And not only that, the Earth itself also goes around the center of mass. So the Moon goes around the center of mass while the Earth is going around the center of mass. So in essence, next time you say the Moon orbits the Earth, you can say the Moon orbits the center of the mass of the Earth-Moon system. So now, the Earth doesn't just sit there and go, I am the Earth, Moon, go around me. No, it doesn't work that way. So the Earth is always doing this. Continuously is doing this. Now, what about the Sun? Because the planets are orbiting the Sun. So the Sun does the same thing. The Sun doesn't just sit there with all the planets orbiting it. The Sun also does this. More than 100,000 miles a year it does this. And so all the planets go around the center of mass of the solar system. They don't go just around the Sun. They go around the center of mass of the solar system. All right, so those are key points there. Now, as the solar system is moving, and let's look at the Sun moving in space. So here's the Sun, and also is orbiting the Milky Way and moving in, Milky Way is moving around other galaxies. So really, this is how the Sun moves. Like a screw. Like that, right? It continuously is doing this. The whole solar system is doing this. So if you look at the entire solar system, they're all moving in space like this because they're traveling and they're also orbiting. And so as they travel and orbit, they keep doing this as they move. Okay, so how do you get the center of mass? Well, you just get it here. Center mass. So here is too heavy. So what do? I put it over here. Move it towards the more massive part. This is perfect now. This is the center of mass of this board. Like that. If I put some weight here, then I need to change it towards the weight. That's how it works.